Hey guys, this video is just a follow-up of the previous one. Um, I said I would do one to cover these last two problems and I completely forgot, so my bad. So we'll do that. These are advanced, so it's totally optional to watch this part. But since I'm already making a video and there's a lot of confusion about this, I thought I'd talk about some diastereotopic coupling and finally put this topic to an end, at least make it make a little more sense. This is kind of my fault because I use diastereotopic coupling and complex splitting too interchangeably, and I think that kind of confused a couple people. So my bad. So let's just kind of finally get this topic totally straightened out, and just make it a bit more clear. Okay, cool. So since we're talking about diastereotopic protons, we should just talk about protons in general, right? Chemical equivalents and splitting and whatnot, and what we would normally expect. So let's say that I had like a propane. Okay, I can make a couple guesses as to this propane's chemical environment and what hydrogens we have just by looking at it, right? And looking for any unique hydrogens and symmetric hydrogens, blah blah blah. So what I see on propane is this CH3. I see a CH2. And then I see this CH3 over here. Okay. Now I notice that this CH3 is symmetric to the other CH3, so I'd expect them to be identical to each other. Okay. So I can make kind of a guess, right? I probably have 6 hydrogens. Okay. A 6H doublet, probably. Or sorry, not doublet. 6 H's neighboring 2 hydrogens, so a triplet. So expect a triplet. And on these 2 hydrogens, right, I have these guys and these guys, right? They're neighboring each other. So 6 total hydrogens. So like a 2H with multiplet, really. Maybe I'll make it nicer. 1, 2, 3, 4, 5, 6. Looks something like that. And, if I ran the NMR, it's exactly what I see. Yeah, probably in this exact order too. All this probably, if I were to label like 0, 1 is probably here, and then, or maybe like 1 is here or something, right? Point is that I can look at a CH2, right, that's unique and say that's a 2H with neighbors. I look in this 3H and this 3H say, hey, they're symmetric, so they'll come together. And they give me one signal, right? And they'd have 2 neighbors, right? So that works out. So currently hydrogens are working out, right? That's working out. We can move up to butane and kind of do the same analysis, right? We could say, hey, okay, let's look at this carbon here. It's 3 hydrogens, which is symmetric to this guy here. And then we have these guys here, right? In the middle, these 2 H's. And we'd have those 2 H's there. Again, symmetric to each other. So maybe we make a guess, right? We say, okay, these 4 H's come together and they are neighboring, right? This 3H neighbor here. So I would expect 3 neighbors, that would be a quartet, right? And also on the green guys, right, there's 6 of them and they're neighboring these 2 H's here, okay? And so what I would expect is a triplet. Now, one thing people kind of often mess up is they think, oh, why did you only count neighbors here and why not over here? Keep in mind that these guys are identical, so they're not going to split each other, right? They're identical to each other, so they're represented by the signal itself. They're only going to split by any neighboring protons that aren't the same. So these guys are going to be split by these guys, right? That would make sense. Okay, cool. So we would do that. And again, if I were to run the NMR of this, I would see exactly that. Right, I would see a 6H and a 4H. So currently hydrogens are working out totally fine. All these hydrogens are perfect, right? They're doing exactly what we wanted to do. But let's say that I took this butane and I added to it this chiral center. Okay, so we have this R center here. Okay, so this is, I guess I could make it a butanol, that's okay. So it's, okay, we have R butanol or 2-butanol. Okay, and I would kind of run the same analysis. Obviously the symmetry is gone, so what I would probably guess is that, hey, I have these hydrogens here, this 3H is different, I have these two H's here that are different. This H here that's different, and then this CH3 here that's different, right? Oh, I almost forgot. I always forget. And then we have this H here. So we would probably expect all of these different signals to show up, and maybe we can even guess, right, what those signals would look like. So this 3H here has two neighbors, so it'd be a triplet, right? This 1H here has 3, 5 neighbors, so it'd be a sextet, right? So I'm trying this to be perfect, but it'd probably be a little more like a multiplet, right? It'd be pre-scrambled. Remember that alcohol protons, because of hydrogen bonding, all that nonsense, we don't really see their coupling. So actually, we can even just resolve this now. We'd have a, 1H that's a little broad because that hydrogen bonding, it makes it hard to read. This 1H over here, right? This 3H here, that has one neighbor, so it'd be a doublet. And then we'd have this green H here, right? This 2H, and this is around 1. 4, so 5 neighbors would be a 5-member, splitting there. So we can make all these guesses, right? And for the most part, right, if I were to run this NMR, this would be fine. This would be fine. This would be fine. This would be fine. But funny enough, the 2H that I drew in green. So actually, let me change this color. But the 2H I drew in green actually is not going to represent itself the way that we've drawn it. Okay. Oh, sorry, I chose green again. What can I choose? Choose orange. Okay. So in fact, this is not what shows up. Okay, we don't see the 2H multiplet. Instead, what we see are 1H peaks. How can I? There we go. What we see instead are 2 1H peaks, right, that represent 2 hydrogens on that carbon, but these peaks are different. They have a different chemical shift. So despite being on the same carbon, these hydrogens are different from each other. And the separation is it's there, right? We can see that they're a bit different, right? If these hydrogens were the same, they'd have the same chemical shift, right? Theoretically, that's how it works, right? If 2 hydrogens have the same chemical shift, they should be, identical, right? Usually that means that they're on the same carbon. But in this case, right, we see here that they're different from each other. So what possibly could be causing this difference? Well, this is the introduction to diastereotopic protons. And the main thing to understand is that if 2 protons are different from each other, right, they have a different chemical shift, that means that their chemical environment are different. Okay, so back here, when we thought about that, right, chemical environment being different, what we were really thinking about was we have CH3s that are either next to CH2s. So that coupling is different from, hey, these CH2s talking to these CH3s. Right? I mean, they're different types of hydrogens and they're in different locations. So obviously their chemical shift should be different. Their chemical environment is different because they're different hydrogens occupying different positions. Same thing with the butane too, right? The CH2, right? Obviously, these are the same because they have the same chemical environment to each other, right? They are symmetric. But if we were to compare CH2 to the CH3, again, different positions, different areas, right? Different number of hydrogens, so they got to be different. So how exactly is it that these hydrogens here are different from each other, right? If they're on the same carbon, they're in the same location, right? Location is not going to help us. Well, what could help is we look at this molecule from a different perspective, right? Let's draw the Newman projection of this molecule. So you might remember that, like, okay, let's say our eye is here, looking this way. Okay, actually, it'll look like this, right? So I'll just sketch this molecule out, but we'd have an OH here, H here, and a CH3 here, okay? In the back, we'd have an H, an H, and a CH3. To help us kind of track everything, I will call the wedge H, HA, and the dash H, HB. So OH is on a wedge, so HA and OH are on the same side. So we'll call this A. Actually, you know what? I know what to do. Let's give these guys different colors. Let's give this guy B with blue and A with green. So A would be here and B would be here. So what exactly is making these two hydrogens different? Well, if we just look purely from, I mean, this here is the lowest energy conformer, right? We have the two largest, or we have the two alkyl chains on the dot and the circle opposite from each other. But if we were to look at this lowest energy conformation, this anti-conformation, what you'll notice initially is, hey, this OH has a different distance from both of these hydrogens, right? Like this OH is very close to this HA, and it's anti to this HB. So one thing we could already take from that is whatever field effects we're going to have, right? Whatever field effect this hydrogen is going to have, or sorry, this alcohol is going to have with this hydrogen here, HA, it's going to feel it the most, right? Versus like if there's any field effect, even if I wonder if we would even feel a field effect from OH to HB, right? I mean, they're anti to each other. Maybe there's some anti-interaction, doesn't really matter. The point is that HA and HB must have different interactions with the alcohol because they're in different positions, okay? So HA and HB can't be in the same chemical environment because HA is experiencing something with the OH. Or on the other hand, right, HB is experiencing something with this H, but HA and HB do not share that same experience. They're doing something else. On the other hand, right, if I just take butane, were to draw that Newman projection, right, just to kind of copy the same thing, right, that would just be CH3, CH3, H, 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 and H. Right? These hydrogens, right, it doesn't really matter if I label them, but all these hydrogens have the same interactions, right? They're interacting with an H and they're interacting with a CH3, right? Interacting with CH3, interacting with H, right? Their chemical environments are the same. Their interactions are the same. So field effects, everything's the same. So that's why we would expect the CH2s on the same carbon, right, to be exactly the same. We're not going to have that same expectation in the butanol, right? HB clearly has different interactions with HA. So this is one way that we can, a bit of a complicated way that we can see, diastereotopic protons or diastereotopic interactions, right? Now, obviously, there's going to be the one student that says, well, couldn't you just rotate the carbon? You totally could, right? So, I mean, it is true that Newmans are not absolute, right? Molecules always rotating. So let's keep the front the same. That's the easiest thing to do. But let's spin the back. So HB is here, HA is here, and CH3 is here. Well, first off, right, these two CH3s being next to each other, I mean, this is very close to eclipse, right? Syn eclipse, which is not the greatest interaction, not the greatest. And then we have HA here, okay? But again, even if I rotate HB into the position that puts it next to, OH, it puts it syn to OH, right? HA is not where HB used to be, right? So HA is also still cis to the OH, just as HB is. So even when we rotate B into a position that makes it similar to HA, HA never rotates in a position to make it similar to HB. Okay, so this rotation doesn't produce an isomer that's exactly the same, right? And where instead of having B and A here, right, it would be like A and B, if that makes sense. Okay, so these two have to be different chemical environments. Even spinning won't save it. Okay, so for simple molecules, you can use Newman projections, right, if you want to. I mean, this is really just for the understanding. It's a bit of a complicated way to do this, but usually the easier way, right, to make this point is you take the molecule that you're studying, and on the hydrogens that you suspect to be diastereotopic, okay, you just switch one of those with D. And you do that with both sides. So we would turn a D wedge here, we'll turn a D dash here. And we get us this. Okay. Obviously, by doing this, we make enantiomers. We make chiral centers. But if I were to look at these two chiral molecules, right, we already said earlier that this would be R, right? This molecule would be R on the alcohol center. But when I look at that center with deuterium, now I don't really need to determine, right, what the absolute stereochemistry is. I mean, I could just, I'll just say that this is R. It doesn't matter if it's right or wrong, right? I'll just say that that's R. But if this center is R and we flip it here, this center must be S, right? Again, absolutely doesn't matter. It's what's relative is what matters, right? If one is this configuration, the other has to be the opposite. If I look at these two molecules, what I make are diastereomers. Diastereomers. And so that's a very good indication that your CH2 will have diastereotopic protons, is if when you switch it with D, you make diastereomers. So you can use this on more complex molecules, molecules where drawing the Newman may not be so easy, right? So yeah, so one kind of absolute true thing about diastereotopic protons is it has to involve a methylene, or it has to involve a CH2, right? There has to be that interaction, right? Otherwise, I mean, you need two hydrogens to be different, right? You're not really going to see that with the CH or CH3. CH3 has 3 hydrogens, right? So, I mean, obviously on this one, like even if I switched one with D, right, this is still an achiral center. So like, I don't know, like let's say I used a butane example, right? And I put a OH here, right? This is never going to be diastereomeric or diastereotopic, because even if this is, this would be S now, but oh wait, is it? Yeah, so, yeah, sorry. Even though, you know, I switch it with D, switching any of those hydrogens with D will still make it, I mean, there's not a chiral center, right? So it's always going to be the same thing. Nothing changes. Okay. Now, actually, I guess what's interesting is let's take that butane molecule and, you know, apply that that trick, right? That trick where, you know, I take this CH2 and I switch one of these with D, and I do it with this one here as well, just as a dash. If I look at the relationship that this new molecule makes, right, clearly we have enantiomers, because the center, if it's some configuration, it's chiral, right? But some configuration will be R. The center is just the opposite configuration, so it's S. Again, if it's wrong, please don't bother me about this. I really don't care. I'm just trying to prove a point here. Okay, so these would make enantiomers. So sometimes some CH2s, right, when they make enantiomers, I mean, if down here the rule, right, make diastereomers, we call it diastereotopic protons. Here, enantiomers, right, we would call this enantiotopic protons. Okay. And these exist in a lot of molecules, okay, where you can switch D and H, right, ends up being a, you know, an enantiomeric relationship. Okay. So why is it that when I did butane earlier, right, I got the peaks I was expecting, right? Why did I not really worry about it whatsoever? Well, it turns out enantiotopic protons tend to be the same regardless. We don't have to worry about them. They have the same chemical environment. I mean, we proved that, right? These have the same chemical environment. But if we were to put this molecule, butane, into a chiral solution or a chiral solvent and run the NMR, we would see a difference. So these guys are going to be equivalent. These guys are going to be equivalent for 118A, because we'll never really see an example where we're putting chiral solution, but it is good to understand that, hey, these are enantiotopic, because maybe you'll be asked in the exam to identify which hydrogens are enantiotopic, and the molecule looks just really normal, right? In this case, we'd have 2 sets, right? We'd have these 2. Okay, cool. All right. On the other hand, diastereotopic are unequivalent protons. Okay. So if I have a CH2 on a molecule with a chiral center, right, that has free rotation, I tend to see inequivalence on those CH2s. Now, in reality, it turns out that that inequivalence is not huge. And so, you know I drew it that it'll look like this. This is like if ChemDraw predicted it, it would draw like this. In reality, what you really see is more of like a sort of like a merged peak or something, or, you know, a really high multiplicity, like really scrambled, really nasty peak, like a complex peak. This is what you'll see in reality, and it'll be like a 2H. And that's just because the splitting is there, but it's usually not that powerful. So unless you have like a really powerful NMR with, you know, a high resolution, you won't really be able to see the peaks really well. But, you know, it should still work out that, you know, the protons are different, right? I mean, the peaks will be a bit complex. Luckily for us, we'll be using, I mean, usually professors use ChemDraw to make their NMR. So like it will predict a really nice clean, even if in real life it's not that clean, right? I mean, ChemDraw as a computer is going to use the best possible magnet, right? It's going to use your computer magnet. Cool. So that's why sometimes you might hear from others, or you might see online, that when it comes to linear molecules that can rotate, diastereotopic protons aren't a big deal, but we still do see complex splitting. Okay, and we'll come back to complex splitting in a bit. Cool. So this is probably like the more like understandable diastereotopic, right? And again, the rule really helps us out here, right? Where we just switch the two hydrogens on stage 2 we suspect to be diastereotopic, and if it makes diastereomers, we will have a diastereomeric center. So what are some other examples where this can occur? Well, another good example is on alkenes. So let's say that I have a terminal alkene. Remember, CH2s are the culprit, right? They're the main culprit. So let's say that I have CH2, and I have these two hydrogens over here. Okay. Why is it that these two hydrogens might not be the same? Well, I could use my switch rule. That's a really easy thing to do, and we can test that out. Okay, I can turn, let's say I turn this into D, and I'll keep this as an H. And then I turn this into D, and I keep this as an H. Okay. Now I know that there's no chiral center here, right? But when I look at my two alkene isomers, one has the D cis to the alkene. So this is sort of like a cis D isomer. The other has my D trans to the alkane. So this is like a trans isomer. Okay, a trans D isomer. You can, for those nerds out there, this is E and this is E, right? Cis trans isomers are diastereomers of each other. We kind of actually saw that in the previous example, by the way. Because if I were to like kind of draw these out, right, where I do the switch rule, right, this is cis trans isomerism, by the way. This is cis and this is trans, although you wouldn't call it that, right? You would use RS labeling, but this is cis and trans. So cis trans is a diastereomeric relationship. And so that's how we can tell that this methylene here on the alkene is going to be diastereotopic. It also makes sense too when you think about it from a rotation, from a rotation point of view, right? There's absolutely no rotation around this. So this hydrogen has different field effects, right? With that methyl versus, this guy has like a hydrogen here. You can also think about it as like how these hydrogens interact with each other is now, they're fixed in place, right? It's not like this hydrogen can rotate on the other side and interact equally with the green H, right? The blue H is probably going to get a different interaction with these guys. Talk about that a lot more in 118b. We can talk about J values and how alkene protons have different J values or different coupling constants or, different talking rates, depending on whether they are cis or trans to each other. So a little sneak peek into that. All right, so we would expect these hydrogens to be different. So that means that this hydrogen talks to this guy, and he talks to this guy, right? So this blue H here would, be about a doublet. So it'd be a 1H doublet. This guy here, right, talks to, again, this guy, that talks to this guy as well. Let me actually put it in the blue color. Let's do this. Although I guess no, whatever. It's okay. Cool. All right. So on the green 1H, we get this. So these hydrogens here, the CH2 on an alkene, we call these geminal hydrogens. For those of you that are into horoscopes, geminal is like Gemini, it's twins. So these hydrogens are twins because they're on the same carbon. Geminal final protons, they tend to couple to each other. What we tend to see for them are these like nice 1H like multiplets, or sorry, doublets. Sometimes though, like if there is no proton here, so let's say, I think I showed this too, right? If we just have these two protons here, we'll see it's like really nice singlets for them. It's because these guys, in reality, their splitting is so small that we don't really see it with our visible eye. You have to really zoom in. If you zoom in, you'll see it. You'll see them like split a little bit, but you have to really, really, really zoom in, right? And not everyone's going to have a microscope, right? Or like a magnifying glass available to them during the exam. But it's whatever. That was just something cool that I wanted to mention. Cool, right? We would expect those guys to talk and have that. But this hydrogen here is interesting, okay? Because this hydrogen, again, also talks to these guys. So let's get this hydrogen to color. This hydrogen talks to this guy, talks to this guy, right? And so from that, it would get, different, and, talking rates are different. And again, how they split is going to be a little bit different. But this guy's also talks to these guys over here. So we also have conversation going on over here. And so this is where that little trick came in that I told you guys about. Okay, because this hydrogen here, obviously, is, it's different from these guys. So it's going to have different splitting with these guys. Splitting with these guys is going to make it, kind of a mess, right? Splitting with vinyl and alkene, vinyl and alkane protons. So for this guy here, what we tend to see, let me draw it this way just to kind of show it, right, how it would actually show on a problem. Right? We tend to see like a really nasty 1H multiplet. Okay, so purple H over here gets a really nasty 1H multiplet. And we tend to see this happen all across like 5 and 6. So I go like 5 and 6 like that. Okay. And obviously where they land is just dependent on the system itself, but this is what we tend to see as a general pattern, right, in the alkene region. Whether it goes up or down, again, is just going to depend on other effects as well. Okay, so this is like a rough rule, right? If you see 2 doublets that are kind of low and then one multiplet's kind of high, that's like our indicator of this like sort of terminal alkene interactions. Okay. Now on the other hand, these 2 H's down here, which again I should put a different color, right? Because they're talking to this H here, right, that's having, it's having all these conversations, right? It's talking to this diastereotopic structure. What we tend to see is some crazy, crazy, crazy coupling, because this guy, again, is talking over here to this guy, and then it's also talking to these guys over here, right? So it's talking to an alkene that has diastereotopic protons, and it's talking to this alkane that has these CH2s here. It's going to have a little wacky coupling, right? Not very clean coupling. So what we'll tend to see is like really weird peaks. So I'm trying to show this. So like, I'll show it to you. I had one like this on here. So like, really weird peak that's like kind of bolded, I like to think of it as. This over here is like around like 2 to 3. Yeah. So this is where that little trick comes in, where if you have an alkene in your molecule or even an alkyne in your molecule, right, because of the weird nature of alkenes on pi bonds and how they talk, right, to other how they talk to other protons, right, what we tend to experience is this complex splitting. So I normally say that this is like diastereotopy. The reason why I use that term is because it's the result of diastereotopic protons all talking and coupling to each other. So my bad on using that. What I should really be saying is that they're complex splitting, right? This complex splitting is the result of being next to alkene. Okay, being next to an alkene. So a very good guess, right, if you want to guess if something is next to an alkene, is you look 2 to 3 and you look for the weird one, like the weird oddball, right? That hydrogen tends to be the one that's next to alkene. Okay, so again, this is sort of, I guess, a way to think about this is like the result of talking to diastereotopic protons, right? This mess here, right? We're talking to all these different types of protons from each other. Okay, so alkenes, because of their lack of rotation, right, or because these H's making different diastereomers when you replace them with D, right, they are diastereomeric. So what's another structure that limits rotation, right, just like an alkene does? That would be a ring, right? So if I have a ring, and let's say that I have something like this here, right, and maybe something like this here, right? Well, now a bunch of these CH2s are going to be diastereomeric, right, or diastereotopic, because their their chemical fields or their chemical environments are different. Okay, just I guess just to make things easy, we can apply just the rule here, right, where we kind of look at this hydrogen here and this one here, and we say, hey, if I were to replace them with D, so let me just do it on this one because I'm lazy, and I'll draw another one. Right. What you'll notice is, oh, okay, so I had these two chiral centers initially. Again, if I just call this R, and I don't really want to do this, but I think this is R as well. But I don't care if it's right or wrong. That would be R. That would be R. If I called this here, what would this be? Is this also S? I don't know. Whatever. I'm just gonna call it S, right? Because the center is flipping S to R, right? This would be different. So RSR compared to RRR, right? Great film, by the way. You guys should go watch that. Right, these are diastereomers of each other. So we can prove with the switch rule that these are diastereomeric. But I mean, you can also just think about chemical environment, right? So if I were to think about like a cyclopentane, it tends to be envelope, right? It tends to be envelope. But if I were to draw out everything on here, right, I would have, right, this ketone here that's up facing up. Right next to it, I would have these hydrogens. And then I would have, right, a bromine facing down, hydrogen here. Did I draw this right? Did I draw this right? Let me check. It's like, for some reason, it's like slipping me. I think it's because it's really late. Something weird feels weird. Oh, okay, I did mess up the bonds a little bit. Oh, wait, did I? No, I didn't. No, I didn't. I'm just being stupid. Oh, okay, now I see what I did wrong. Or why it felt wrong is because these should not be like this. They should be more like this. It's a little bit different, whatever. Anyways, I wasn't totally wrong. Doesn't matter. So it was H here and PR here. Okay, and again, let's do that thing where I'll just call one of these HA and HB, right? Doesn't matter who's who. Call this HA and we'll call this HB. Right? Again, if I look at the field effect, right? If I look at the chemical environment, things are different, right? If I look at sort of the wedge face of this molecule, right? HA has different interactions because, I mean, it will interact differently with this ketone, right? And with this H, versus HB, who has like this bromine in his face and it's kind of hard to see, but it would have that hydrogen there, okay? And then its distance from that hydrogen, right, might have a different effect, okay? So again, looking at chemical environment, obviously HA is different from HB, right? They're not even near the same things. So this is why ring CH2s tend to be diastereotopic, because when we look at what's around them, they're different usually, right? There's like different groups. Now, obviously, if I have like a cyclopentane, and I were to look at these hydrogens, right? The conversation is a little bit different, right? I mean, if they're just H's here, I mean, obviously then they're just experiencing all the same H's, right? It's not really much changing. Right? They're all just experiencing H's, so obviously then all these would be the same. But if I add a group, right, on the molecule, things start to change, right, depending on where it is. So Q to the problem that seems to stump everyone a little bit, but let's say that I had, right, this molecule here. So unlike everything else, right, this molecule has no chiral center. Right? If I draw a planar, right, it would look like this. But again, remember that these molecules are 3D, so whether it's wedge or jazz, I mean, whether it's wedge or jazz is the same, doesn't really matter, but we can just place it somewhere. I'm just going to place it on this face here, right? If I were to again look at the H's, right, how the H's interact is going to be different, right? Because again, this hydrogen that's up here will have a different interaction with the carboxylic acid or with this H here than this H down here will, right? Now, if we look at this side, this is the same, right? They're both interacting with an H, so we don't really care about that side. What we do care about is that, hey, we have this carboxylate that's facing up, or sorry, carboxylic acid that's facing up, and that's going to have a different field effect with these hydrogens here, right? We'll have a different interaction with them. So those hydrogens are going to be a little different. Okay. Now this would be a case where the shift would probably be very, very close, but it would still be a different one. We would still have a different estimation. Or a different chemical shift, sorry, on these hydrogens. Now, these hydrogens, it's a bit more difficult, right? It's a bit more difficult to say because, I mean, really their chemical environment is just these other H's here. And, depending on the actual like crystal of the molecule because we don't really know what the actual distances are. If I were to draw this like a bit closer, right, it's very possible that we can make the argument here that, hey, if this carboxylic acid could reach, like, let's say it's facing up. I might have made it a little too much, but like, let's say that it is facing up, right? And I were to have, a bit of a longer bond on this, right? Like maybe a more realistic bond. I don't know, whatever. Point is that we don't really know. Right, let's say I draw that H there so you get that bond. I mean, this could be an interaction that makes it different as well, right? Because this H is a bit closer to this one. This H is a little bit farther, right? That could be a possible effect. I wouldn't bank on this being a huge effect, but it would still count towards, making this slightly different. So these H's just by default might be slightly different from each other. I would still expect them to kind of overlap. Like it would be like a 1.17 versus like a 1.30 kind of difference, or maybe that's a little too big. But you kind of get my point, right? Like they would be different, but slightly different. Okay. I don't expect on your exam to have something that's difficult, or you could have something that's difficult, right, of question, but it's a good thought process question, right? On your key, it does indicate that these two hydrogens are different. So why might that be, right? Think of a good reason. Good reason might be, hey, maybe this hydrogen here is doing something weird, right? Maybe it's having an extra interaction with these guys, right? And the distance is different, right? One is closer, so the interaction is more pronounced between these hydrogens versus these hydrogens. Just food for thought. Okay. So chirality, right? Chirality in a ring is not really important, right? Because, let's actually apply the rule, right? Let's do that rule where I change one of these into D, right? If I change one of these into D, notice how adding that chiral center, right, that D center makes the carboxylate center also chiral. So if this were a wedge, for example, right, versus if this were a dash, right? Let's say this is like an R center, this is an R center. Let's say this is R, this would have to be S, right? Because they have to be different. These are diastereomers. So true really is like your final, or like you could just use this always, even if you don't understand it, and you can still get this right because this will make diastereomers. Same thing with that CH2 down here, right? So theoretically, this CH2 down here, if this were a wedge, right, would have to be diastereotopic, because when we add it in, right, these are diastereomeric centers, or sorry, this would make it diastereomer, right? Like again, if this is R and I don't know, this is like S or something, then the other one would have to be R and R, right? I want to draw it out, but it would be R and R. So theoretically it checks out. So if this like 3D stuff doesn't make sense, or it's like kind of hurting your brain, just use the rule, right? The D rule works pretty well. Okay. Cool. So hopefully that helps you guys understand diastereotopism and how to kind of test for it. It kind of helps you out with the shifts. In terms of NMR and chemical equivalence, right? What it means is that a CH2 has the potential of having two different hydrogens, right? Most CH2s have like a hydrogen A and a hydrogen A, they're the same. But diastereotopism, tells us that we can have two different hydrogens. So how can that represent in the NMR? Right. Again, one way we see it is we see sort of like two peaks, and one kind of nice thing is that they tend to mirror each other. They're like 1H, 1H. And, these can represent a CH2 on a molecule. For example, maybe this 1H, 1H is like this guy down here. Sorry, let me try these back in. I just want to take out the arrows, right? Maybe this 1H, 1H is like, this is HA and HB, right? It would depend, one of these H's would be HA, one of them would be HB, and you can see that the shift is slightly different depending on their interaction. I actually always forget this all the time, but usually the rule of thumb is that the one that's closer, so like this is the chiral center, right? Oh, actually this one's a bit difficult because there's two of these, but generally it's the hydrogen that has more hydrogen interactions, right? So it's interacting with more hydrogens, tends to be the one that's more deshielded. That's like the general rule of thumb. But not that you guys need to know that, not just quite yet. But usually, one representation is we have, two different 1H peaks for a CH2 than we expect. So we know that there's some sort of diastereotopism happening. right? This would be like for a ring, right? And depending on what it's around, right, the chemical shift can change. So in this case, for this carbon, like this is bound to carbon and carbon. I mean, maybe around 2 because it's like kind of close to bromine, whatever, like it's around 2, but like, somewhere like 1 to 2. So I'll put like 2 here, or, 1 is over here, like 2 is here, something like that, right? It's relatively boring, these hydrogens. But something like an alkene carbon, right? An alkene CH2, I mean, those are going to be all the way up here, right? All the way up at 5 and 6. So again, we see those 1H is splitting off, right? One a little more detailed than the other, and this is something that we won't understand why until like 118b, but one will always be detailed than the other, right? And then we have that 1H multiplied if it's terminal, right? So if it's terminal and it has this purple H, we'll see that there. Right. Again, a good way to identify the CH2 next to the alkene because of diastereotopism is, the complex splitting of some proton 2 to 3, right? Because this position, this pink position here, remember we called that the alpha position, and alpha position hydrogens tend to be around 2 to 3. Okay, so a nice little trick. It'll work about 90% of the time. Okay, cool. All right, so that's diastereotopism. We'll call it on that. If you guys have any more questions, obviously let me know. I'm more than happy to answer them. But let's get on with these NMRs, right? Let's kind of finish this out. So we'll do the first one. And so actually, if you look at both of these NMRs have something special about them. That's what makes them hard. But we'll do this one first. Okay, but you can do your DOU. I should actually do it too. 10 times 2 plus 2. Plus 0 minus 1 minus 11. So we're 2c plus 2 plus n minus x minus h, and then all over 2. Okay, so 22 minus 1 is 21 minus 10 is 10 over 2. And this is 5 degrees. So just a bit of a short reminder, right? 1 degree is a double bond or a ring. 2 degrees is any combination of 1 degree. So ring, 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 double bond. Sorry, why did I do that again? Ring, ring, double bond, or double bond ring. It can also just be a triple bond, just one single triple bond, right? 3 is any combination of that. 4, remember, is the nice number, right? If you have at least 4, you might have a benzene ring. And an easy way to check is just to look from 6 to 8, right? If you see any coupling, it tends to be aromatic coupling. So in this case, that's what we're going to see. We're going to see aromatic coupling. So 4 degrees go into our benzene ring, and we have a last degree, 1 more degree, right? If I look at my IR, right, this here is just my sp3ch. I see a 2750. Okay, so that's a bit interesting to me. But I also see a 1650. That's just C double bond C, right? That's probably coupled, that's probably the alkene there. And then sp2ch, right? 31 and 6050, I'm thinking that's the alkene, that's the alkenes in the benzene ring. I think my last degree is being explained by this 2750, which gives me, aldehyde vibes. Remember, you don't need to look in IR to prove there's an aldehyde. Just look at your NMR, right? If you have a 1H singlet, a 1H anything, not a 1H singlet, I just, my bad, it's because it says singlet. But if you have a 1H, it's around 10, that tends to be aldehydic, right? Tends to be aldehydic. A very good question I got recently was, how do you tell the difference between aldehyde and carboxylic acid? Carboxylic acids tend to be a little north, or a little, west of 10, and they are also rounded because they are alcohols, right? Or not alcohols, but you have an alcohol on them. Okay, so that's why we don't see, that's why we don't really see this guy, or that's why we don't really predict this guy to be in here. Okay, but this is definitely an aldehyde. So I can put an aldehyde here. Okay, and I definitely have a benzene ring. Okay, now before, when we had a benzene problem, right, what we had was a 5H, right? So I think it was like the second problem on here. It was a 5H. And that meant that, hey, I have 5 hydrogens, right? All kind of on here, and then 1 position for a carbon chain to be, right? So let's figure this out. But when I look here now, I have 3 hydrogens. And so 3 hydrogens means that I have 3 positions that are not hydrogens. But I can't just say that it's, a pattern just like this, where I put 3 hydrogens next to each other, and I put three methyls next to each other, or three possible positions like can be added onto next to each other. Because, well, this is not the only possible arrangement, right, of three hydrogens. I can have a couple of arrangements. So whenever you have three hydrogens in your benzene region, here are the different types of patterns. And I'll try to put these in an order that is like, you know, easiest to hardest to see, so that you can do the easiest ones first and then do the hardest ones later. But the easiest one to see is when we have this sort of coupling, or this sort of pattern here. Okay, 1H's that are all separated by some carbon group. Okay, why is this the easiest? Well, if I kind of use my neighboring rule, right, all these hydrogens are kind of blocked off by these carbon chains, right? They don't really have any neighbors. So what I would expect to see is three nice 1H singlets. Okay, wow, easiest thing to see, right? And actually that's what we see here. So we have immediately solved for what our benzene structure looks like. Okay, but I mean, we should still look at the other ones, right? Because I can't guarantee, nor should you just accept that this will be the one that you get, because you can get a harder one for sure. Okay, but luckily for us, this is the easiest possible one to see. Okay, this is going to be our splitting, our substitution pattern. Okay, but again, three singlets tells me that my H's are all separated by some carbon group, right? They can't split each other. Now, let's say then I keep two of these hydrogens the same. So maybe I keep this here and I keep this here, right? So these hydrogens stay the same, but this hydrogen on the bottom right moves in a little bit closer. Okay, so now that I get this, okay, now I have two hydrogens that can couple with each other, and I have one hydrogen that's all by itself. Okay, what would this look like? Well, no, let me give this, sorry, I wanted this to be this. Okay, what would this look like? Well, we would still have a singlet, right? We'd have a 1H singlet, but now we have two hydrogens that can couple to each other. So we might expect there to be, right, 2H doublets, or sorry, 1H doublets, not 2H, 1H doublets, right? Now, I'm just randomly putting these guys next to each other, right? I'm not exactly doing this as correct as possible, right? Because I don't really have any idea. Like I don't have any idea to, without knowing what the substitutions are, how these guys would be laid out. But what the most important thing is that there's only one singlet, right? I mean, this could have also been in the order of, right, two of these guys, and then like this, right? So 1H like that, and then 1H, 1H, right? That's also a high possibility, right? All that matters is that you kind of recognize the pattern, right? There's a 1H that's a singlet, and then we should have kind of like doublet 1H's, right? Because that's what would make sense when they're splitting. Okay. I don't know why I drew these in a different color, actually. I didn't draw the other H's in a different color. So I don't know why I did that. Probably just a very late night brain fart. Okay, so again, it could have been that the 1H is crowded. It could be the 1H is at the top. It could also just be at the bottom. Really, the only thing that determines this is what these groups actually are. So this is an advanced topic, but depending on the identity of these groups, we can actually determine how the 1H's would arrange around each other, but not something we have to worry about. Point is to look for the pattern, right? The pattern is that we have a 1H singlet, and then 1H's that are not singlets. So if you have a single singlet, right, but we know that there's three H's in this region, it's got to look something like this. The last pattern is the one that I drew first, and it's by far the worst one to have to look at. Okay, but we can have this 1H, 1H, and 1H. Okay, and this one sucks, right? But what's nice about it is that all these hydrogens are coupling with each other so that there isn't a singlet. So there's kind of two ways you can imagine this represents. In a perfect world, right, we might expect to see, these two hydrogens are coupling, so probably some kind of like triplet, or maybe like some complex split. So I'll just draw a triplet to just, have it there, and then two doublets, right? Really, what we would probably expect for this middle one is something called a doublet of doublets. So we'd probably see something like this. Okay, and the reason for that again is diastereotopic coupling. Okay, so we probably expect to see something like that. But the point is that I want you guys to see here is that there's not a singlet, right? If there's 3H's and you don't see a singlet at all, right, you can kind of default to this pattern, right? Because I mean, no singlet means that all the hydrogens have to be crowding each other somehow because they're all coupling with each other. So I guess in a way, maybe this is not that bad. It's not that hard, right? I mean, obviously I tried to put it in the easiest way, but it's not too bad to see either. Okay. So again, don't try to memorize these. Like, look at my logic for them and how I'm coming to the conclusion that these things would look like. Because I can't guess what's going to be on your quiz or on your exam, right? But I can tell you, ways to make good guesses so that whatever you get on your exam, you'll get it totally correct, right? Because you have great fundamentals. And you're learning from me, so you're going to have great fundamentals. Okay, cool. So these are my 3 different 3H arrangements. The next question we'll consider 4H arrangements. So we'll cover that. And then we could technically do like a 2H arrangement. Well, maybe we'll cover the next one. We'll see. But these, again, I don't really want you guys to sit here and write these down and memorize them. I just want you guys to understand how we're coming up with the chemical, or what's the intuition we have behind understanding if I see certain peaks here, how I can translate them into an answer. Okay, but again, with that being said, I'm fairly certain my benzene is trisub with this pattern here. Okay, so I can start to put things around. Sorry, I don't know why that was a carboxylic acid. It should be an aldehyde. But we have an aldehyde. That's the first thing we know, and it's a 1H singlet, which means that whatever's here has to have 0 protons. Just a reminder, very good thing for that. We could put like an oxygen. Sorry, we could like an oxygen. That's a 0 hydrogen structure. We can put like a carbonyl. That's a 0 hydrogen structure. Right, just spitballing really, right? We could put like a terbutyl, right? There's so many things that we could put next to a proton so that it has 0 neighbors. But the one thing that I notice is that we already kind of have a group that does that, right? We have a benzene ring. So my first guess, not really even a guess, I'm fairly confident in this, right? Is that the benzene ring here is going to be connected to the aldehyde, because that's a good way to give the aldehyde 0 neighbors, right? So not a bad guess. And I do have to put 3 things around it, right? So this is a good way of getting those out of the way. Okay, so how do we retry these hydrogens then? And underline these. Again, I don't really know which one is which, but I don't really care, right? I just wanted to get the pattern down. Let's make this hydrogen this color here. Cool. So now I have 2 different chains. Looks like I have a bromine and an oxygen left. Just got to figure those out. Oxygen might be the easiest thing to deal with, right? Because it's the most electronegative. So when I think about my 3 specific pieces of information, I'm not really worried about, which one might, associate with which peak. So what I think here is that I have an oxygen that's going to be, well, I guess actually first thing I'm going to ask is, how do I know what kind of oxygen structure this is, right? There tends to be 3 of them. It can be a carbonyl, it can be an alcohol, it can be an ether, right? Which one do I think it is? I think that it's going to be, obviously it can't be a ketone because we've already used, we have an aldehyde. That's the only carbonyl we have in this. And there's no alcohol peak in this. So I think it's going to be an ether. So there's going to be hydrogens on this side and this side usually. And again, if I look 3 to 4, most electronegative peaks that I have left are 3H singlet and this 2H triplet. So I'm going to assume that on one side of this oxygen, there is going to be a 3H singlet, just like that. And then on the other side, I'll assume that there is going to be this 2H triplet. Okay. Now, again, what's so nice about oxygen is that if I have a triplet, obviously no neighbors are here. They've got to be here. So I know that the last remaining 2H that's seeing this, it's got to be over here. Right, and whatever's here again has to have 0 neighbors because this 2H triplet is coupling with this guy and this guy is coupling with this guy, right? So they're triplets of each other. So maybe that's a nice little pattern to have written down, right? If you have 2 2H triplets, right? This is a possible interaction they have, right? Again, I have a 0. I need to put a 0 structure here, 0 proton structure. If I just do what I did last time, I'll just, sew this on here like I'm Coraline or something. And I'll go ahead and put this on like that. Okay, so I've kind of resolved all my hydrogens, and I have only one position left, and I really only have one atom left after the bromine, but I can fairly, easily come to the structure right here. Okay, so this structure wasn't too bad. I tried not to make it too hard. Oh, interesting. Okay, so I just noticed something. There can actually be another answer to this. Okay, this one's actually, okay, this one's a little more difficult. This one would be a hard one, so you would never expect to see something like this. I just realized that, well, okay, if we go with the assumptions that we always gone with, that electronegative things are next to it, are really high up, and usually the first things to resolve, then this works out. This should be the answer based on what we've learned, right? But we could also potentially make a structure where we assume, so let me draw the structure that because I think this is actually what I generated. I think I actually wanted it to be this. I think I wanted it to be this here. I'm just having like something just feels weird about this molecule. I feel like this isn't exactly what I wanted it to be, but it's okay. Point is that this has the possibility of two answers. But this one would be fine. So this is like an instance where I call this sort of like NMR blindness, is when you generate a molecule in your mind that you think is really good, but you don't actually sit down and try to make it. And when you don't do that, you may not realize that the problem is trickier than it may seem, because this is at least with what you've learned, is a way better fit for what we see on here. This is really, really tricky because, it's really hard to tell that this 2H was actually supposed to go with the bromide. Okay, so I think this is the one, I'm pretty sure this is the one that I want it to be, but this will work, right? This is okay. I am okay with this one, okay? I am okay with this one because, we used our chemical intuition to get to here. I imagine if I put this one in the NMR, like in ChemDraw, I imagine it would just it would probably be very much the same. It probably wouldn't be too different. I think maybe this 2H might be slightly more shifted up, something like that. Again, yeah. Cool. Anyways, so that's the first one. Main point there is just the splitting pattern, right, on the benzene and how to logic through these, right? So let's go ahead and look at the last problem here. Another benzene. I'm pretty sure there's 5 in this one as well. I just don't want to go through it again. I'm pretty sure there's 5 degrees in here, right? There's the benzene, so that's 4. And then we see activity 5 to 6. Maybe you guys recognize this pattern. I don't know. But that's an alkene right there. So let's just talk about the benzene real quick. So we have 4 hydrogens, 6 to 8, right? You remember, you can kind of ignore this one, right? You can tell that these guys are aromatic, right? They're 7 to 8, so there's aromatic stuff going on. But this is if we have 4 hydrogens. And so there's, again, 3 kind of scenarios with those 4 hydrogens, how they might orient themselves. Okay, and I'll try to do it from easiest to hardest. Okay, but the easiest one to see is when the hydrogens kind of group like this. Okay, so why is this the easiest? Well, first off, this is symmetric. Okay, so let me put these in a different color, but these hydrogens are symmetric to these ones. So because of that, it turns out that this benzene splitting pattern will actually give us a 2H doublet, right, and a 2H doublet. I used to have a name for these that was not a very good name. It was kind of like a joke name. You can probably figure it out. I won't say it, but there's a way to remember this. But if we see sort of 2 identical 2H's, right, that they're sort of these 2 towers here, sort of like that national tragedy. this is going to be what we call this splitting here, where the two groups are opposite each other. And the cool thing is, because the line is going through the groups here, actually these groups can be anything, right? They could be X and Y, they can be different. If they're different, right, then the symmetry is still valid. It doesn't have to be that they're the same group XX, right? You can be XY. They're on the symmetry line. So this is always going to be symmetric. So the 2H identity is always preserved, right? Even in symmetry, or even when there's symmetric groups, or asymmetric groups, is what I should say, sorry. Okay, so this is the easiest one to see. We actually have a name for this called this para. Okay, cool. So then let's say that we shift over the alkyl chain 1 over, right? So let's say we shift it over 1 on 1. What do we see now? Well, kind of like in the 3 H's, right? We see an H that's kind of flanked by 2 groups. And whenever that happens, remember, we get a singlet. So we'll definitely get a 1H singlet. We also have these 3 H's like coupling each other. So maybe we see like other coupling. So this guy will couple this guy. Maybe what we see is a doublet of doublets again, right? We'll see like a doublet and a doublet. Again, it doesn't matter the way this is arranged, right? That's not the point. What the point is, right? The point here is that we have this one singlet that's ringing out. Okay, again, looking for clues on, what structure is valid. Right? This is possible if you have 4 H's here, right? If we count 4 hydrogens in my aromatic region, right, and I see a singlet, I want to probably do this, separation here where one of them is like isolated from the rest. Call this meta. Okay. The last one is if we put both alkyl chains next to each other. H here, H here, H here, and H here. Okay. We call this ortho. And as you can imagine, there's no singlets. It's just a mess. Like everything is coupling with each other. So you tend to see like a bunch of peaks. And I mean, I'll draw them nicely, but they're not really going to be nice, right? We'll probably see a doublet and doublet, and then we'll see like doublets of doublets, and again, doublets of doublets. So, right, some nasty stuff. The point is, it's just like with the 3 H's, right? We don't really see any singlets, right, or anything. We don't see any nice indicator like the 2H or the singlet. So we default to ortho. In that case, we call this ortho. Okay. So again, just thinking about ways to rationalize what these groups look like. Now, actually, now I think about it, I guess these two here could have a little bit of symmetry if like the groups here are the same. So let's say this is XX, right? There would be symmetry here. Oh, this would be kind of crazy because this is a 2H doublet. Oh, huh. So how could we resolve this? Usually in this class, you never really see, we never really see this kind of like symmetry going on, but you never know. Maybe she might get like, ooh, like we should have like a, I don't know. I'm just saying things at this point. What can we expect? I mean, it would be a 2H. I guess I'm wondering what the coupling would look like, because I'm not entirely sure. I've never really seen something like this before. Oh, you know what? I have ChemDraw. What am I doing? Just use ChemDraw. See what ChemDraw says. It's actually, okay. So it's a learning experience for both of us, for me and you guys. Okay, so it turns out ChemDraw kind of says it's the same. It is going to be kind of like a doublet kind of thing. It just looks kind of ugly. Okay, hold on. Let me just new share. Cool. Okay, so I just went ahead and put bromines on a benzene. So this would make the 2H, but you can see it's a little bit uglier. It's not the same. Actually, what if I had made these like ethals or something? Right. Oh, yuck, look at that. Yeah, I don't think this is likely. You can see just like kind of, only see it just kind of morphed together. I guess you'd have to bank on the fact that these would be symmetric, right? But they would be symmetric ethals. Damn, this would be a hard one. A really hard one. What if it's meta? Because that could also be an issue, right? Oh, yuck. That's disgusting. I don't want to look at that. What if I make this oxygens? Oh, you can't even see anything. I made these bromines. Oh, okay. So it's like a singlet, and then yeah, you have a 2H and a. So this would be a 2H, and this would be a 1H, right? So you'd have the singlet you'd expect, and then you'd have a 2H, right? And then a 1H. So 1, 2, 1. It's the only way that this would work. So it'd be 4, but it's not a pattern that we I guess, I mean, it still follows the meta pattern, right? That there's a single singlet. So you could still figure this one out. Okay, cool. So hopefully, for fingers crossed, you don't get something weird like that. But yeah, so let's just solve this problem first. 2H doublet, right? That's going to be our pair splitting. So we know our 4 hydrogens are like this. So we have to have something here, something here. There's also an alkene because there's activity going on. We can see that there's 3 hydrogens in this region. There is this 4th hydrogen here, but we can kind of ignore it. So let's kind of get rid of it for a second. It's an alcohol, right? It's broad. So just draw an alcohol here for a second. So we can ignore it. But if I look here, I have a 1H, and a multiplet. We talked about this, right? These 1Hs are very close to each other. They're just splitting because they're distereotopic. So we have an alkene with a CH2 at the end. And then we have this multiplet. So whenever we have 3 hydrogens in this region, this is going to be a terminal alkene. Okay, a terminal alkene. Now, another little trick that we can use, so actually I can literally tell which H is which. This, this, and this. I don't really care which one's which, honestly. I'm pretty sure it's that, but whatever, it doesn't matter. Okay. And we talked about this, right? If there's any hydrogens here at this position, right, they would show up 2 to 3, the alpha region, right? And they would also look kind of messy or complex, right? Because they're interacting with a diastereotopic structure. So if I look 2 to 3, or I mean, if I just look here in general, right, that's the only peaks I have left. I'm looking for a peak that doesn't look very good. I see a peak that I think is super, it's like, you know, it's like Schrodinger's peak, right? And who knows what it is, right? I put doublet just because I put doublet, but I think that peak looks really weird and it's messy. So I'm going to guess that it's the one next to the alkene. Yeah, very, very good guess in my opinion. So I'll put this here. Now it's a doublet, so it's interacting with 1 hydrogen, which is this guy here. So whatever is here has got to be a 0 hydrogen. I have a benzene ring. That's the best 0 hydrogen structure here. Okay. So go ahead and put this here. And all I have left is an OH and this part here. You know, if you could just put the OH there, but you have 2 H's that are still left over. You can kind of think, you know, there's a good way to rationalize this, right? There's a 2H triplet that I'll just put next to the alcohol because it's all the way up, you know, between 3 and 4. So CH2 there. It's a triplet, so there's the CH2 next to it, right? So let me write this out, sorry. There's a 2H here at 4, so it's probably next to the alcohol. And it's a triplet, so it's got a neighbor, right? Probably just going to be the last 2H here. And so again, this 2H is triplet coupling with this guy, it's 2H. So there's 0 neighbors here. I mean, only one place it can go, right? It's got to go here. Cool. All right. So there you go. That's the complex ones. These are like 118B level, but you can see that even a 118A student can answer them. You just have to use your brain a little bit. All right. So again, you know, what I really want you to take away from this is how do we rationalize the aromatic splitting, right? Don't memorize all that stuff. It's ridiculous. What you should know is, hey, if I have a benzene ring and I know how many hydrogens are around it, right? How can I rationalize what the structure is, right? Like let's say that I think the structure is this, right? What should I expect from the structure, right? What should I expect to see from a structure like this one? What should my splitting pattern be? I think that this one here is a fairly obvious what you would see here, right? Probably see a singlet, right? Because these both are the same and they have no neighbors, right? We have symmetry, right? Would that symmetry work actually? Yeah, it would. Right? It'd be like a double pair kind of thing. Yeah, it would. Wait, would it? Oh, I guess that's dependent on, now my brain's hurting. So what I just did was bad because I assumed that these were the same, right? That's the only way this works, right? Right, because then if I flip on that, brain hurty. So I guess if they're symmetric, then this works. Or I guess at least as long as one of these are symmetric, right? Because this could be X and Y, and I could do symmetry down this way. Wait, what? I'm being stupid. Sorry. God, I can't even cut this out. It's just late. I'm being stupid. I don't know why I'm drawing all those lines. Whatever. Let's see. These are different groups: A, B, C, and D. There is no rotation, right? Because I was thinking of the reflection the wrong way. My bad. Yeah, so I'd probably expect two singlets here, right? 1H and 1H. But if all these groups are symmetric, then you could expect a 2H out of these, right? This is a single 2H peak. So I could rationalize that, right? Or maybe I have something like this, right? Where I have a 1H here and a 1H here. Oh, yuck. that is especially disgusting. If I, let me put the A, B, C, and D. That way I don't make any stupid mistakes again. A, B, C, and D, right? Okay, clearly no symmetry, but these will also just be singlets. Oh, I guess the 2H is a little bit harder because this will also be two singlets. Whatever. Anyways, so you'll probably never see those guys, luckily for us. But again, like if I were to try to rationalize my 3H structures, right? How we would do that. If I want to rationalize my 2H structures or my 4H structures, how would we do that? Things to think about. Okay, cool. All right. As always, if you have any more questions, just let me know. For those of you that made it this far, I'm actually considering making a synthesis video. I guess I just need to know how good the one was that was provided by the